Okay, so then I will do that. My video is coming, right? Okay. Yeah, so very good afternoon to all the attendees of this NPTEL course. I am Dr. Rishikesh Bharti. I am a faculty member at the Department of Civil Engineering, IIT Guwahati. So I hope you are enjoying this course so far. So this remote sensing and GIS course, I tried to make it so simple so that anybody can start learning these topics, and subsequently the advanced topics are covered so that you can start your research as well. So before I start with the doubts, I have a few things to say. Like first one is, before asking your question, please read the forum discussions, because you might be having a question which already others might have asked. So please do not immediately write the or send the query. You first follow the discussion which is happening in the discussion forum, and then you put up your questions. Then please ask your questions well before the due date of the assignment so that we can answer it. Otherwise, what happen if you are just asking this before the deadline, we might miss to check the emails or the doubts, and then you will miss the deadline. And some of the questions in your assignments are conceptual. You need to use the concepts explained in the lecture to solve them as per the guideline of the NPTEL. Conceptual questions are mandatory, right? And that can be from my lectures as well as the suggested extra readings. So we are following a protocol. So these conceptual questions are part of your evaluation. And do not ask the same questions from your assignment. You will get no reply from our or me or from my team, because there we will that questions will be evaluated, right? So if we tell you the answer, then there will be a problem. Now lecture notes are available through NPTEL. No PPT PDF will be shared. Please read the books and follow the lecture videos. And enough materials are available in the intranet or internet. There you can just search good books, which I have already given you the list, and you can find that. Or maybe you can go to some library where you can have the access of these books. And somebody in the discussion forum asked like very basic physics and math question. So it is expected that you are familiar with the basic physics and math, especially 10th, 12th level maths and physics. So these questions, please refer to some standard book and clarify your doubts. And one more thing, which is very important, and many times I receive this request, that software related demonstration. So in this course, basically what I tried to give you the physical meaning, or I wanted to make sure that you understand the physical meaning of all the topics, right? So if you understand what is happening at the background level, you can use any software or any tool. So to know the content of the course, please refer to my first lecture video, where I have given you the full list what are the topics will be covered. And somebody have asked a few queries I received related to histogram equalization. So just wanted to give you a overall understanding, like you can understand through these slides. So when we talk about the images, when we capture it from the space, because of the atmosphere, because of different errors which are associated with your measurement. And because of that, display might not be very, very good, because when you take a photograph, let's say you take a photograph using your mobile phone or camera in the evening, and let's say that evening is very warm, or having the humidity more than 80%, you will find that pictures or the photographs which you are taking, it is not of that good quality. Why? Because the atmosphere is playing that role. So here, when we talk about the histogram equalization, this is the digital image processing technique, where we want to remove the error, or we want to make our image more clear, so that our objects can be identified, or the image will have very good brightness and contrast. So this is histogram equalization method. An image is transformed in such a way that all the gray levels are having equal likelihood of occurrence. That means when we talk about the histogram, let's say this is the histogram. This is the histogram of my image which I have taken or captured using my mobile phone, let's say. But here, if this is a 8-bit data, 8-bit data means 2 to the power 8. That means you have 256 gray labels option. Now, considering this first point is 0 and this is 255. So this image is occupying only the central middle range of this. That means this much space is available, and this much space is available at the end. So this is not a very good histogram of an image. So if this histogram is occupying this whole range, that means it is occupying 0 to 255. That means 256 gray levels. Then we can say this is a very good histogram. And if the histograms are well distributed, then we can say that our image is having good brightness and contrast. And if the brightness and contrast is good, your image will appear better. So in histogram equalization method, image is transformed in such a way that all the gray levels have equal likelihood of occurrence. Histogram based enhancement technique considers the relative frequency of the occurrence of the gray level. High frequency gray levels should be given preferential treatment. High frequency means, here the frequency doesn't mean the DN number. The frequency is the how many times it is occurring in your image. So how repeated time, how many times it has appeared in your image. So high frequency gray levels should be given preferential treatment, so that they should be well separated on the gray scale for better display quality. So using this concept, what we do, we try to make this histogram as this one. And once we do that, our images will be better. So for that, we have this formula where we are using the CDF value, cumulative distribution function, right? And M and N is the image number of pixels, and L is the quantization level, that is 8-bit, that means it is 256. So here the minimum and maximum will be 1 and 255, or 0 to 255, or 1 to 256, right? If you do that, let's say this is your image, and these values are nothing but the digital number associated with your individual pixels. So based on these values, or the variation in these values, you will have the objects appearing brighter or darker. So if you do this calculation for the DN number, this is from the matrix which we have from the image. From here, we have identified the unique values, and we have put from 43 to here 75. And this is the frequency, how many times it has appeared. So 43 2 times, 44 2 times, 45 1 times. Then we have arranged in the increasing order. Now this is the cumulative distribution function. So starting with 43, it is 2. Then we will add 2 plus 2 is equal to 4. Then here this is 4 plus 1, 5. 5 plus 1, 6. 6 plus 4 is equal to 10. So like that we have calculated, and this will come 144. So there is a cross check. Now you know the size of your matrix. Let's say this is 12 by 12. So if it is 12 by 12, then this number CDF value should match with your M cross N. If it is matching, that means your calculation is correct. Now, again referring to this, if you understand this particular concept, doesn't matter which software, which tool you are using, you will be able to do the histogram equalization. But you will also understand what exactly been done at the background level, right? So after applying this, so this is a raw image. And once you apply the histogram equalization, you can see how beautifully they appear, right? After histogram equalization. Similarly, this is another example. You can see here. The next topic was like many people have asked about the PCA. So why exactly we need the PCA or any analysis related to what PCA is doing? So here you need to understand a sensor is a bundle of detectors, right? If it is a bundle of detectors, what is their role? They are responsible for generating the pixel values, the DN numbers. And these pixels are, these detectors are having some sensitivity. Let's say we are having a sensor which captures between 400 to 2500 nanometer. Now, between this range, we are generating 5 or 4 bands. So there might be some wavelength region which are left, but some might be 400 to 450, one image, then 450 to 500, next image. So if you see 400 and 400, 400 to 450 and 450 to 500, there might be a possibility that some of the information which is available in 400 to 450 band, the same type of information will be available in 450 to 500 bands dedicated to a particular feature. So what here we want to do, since we are capturing more number of images or bands by a single detector or sensor, we want to remove the data redundancy. The data redundancy we have to remove. So for that, we use the PCA. So here, what we will do, we will decorrelate the data sets. So in general, band acquired in different wavelengths are correlated. Highlights reduce the data redundancy. The number of output principal component image will be less than or equal to the number of output band. That you will understand afterwards. Highlights a specific feature using their responses in different bands. Now here what advantage we have? One particular feature will be highlighted by taking inputs from all the available bands. So if you do the PC analysis, the principal component 1, 2, 3, 4, depending upon what was your input number of bands, your output will be decided and features will be highlighted taking the information available in different bands. So the background of the PCA I have already covered in my lecture and I have covered in very detail. So I don't think there should be any problem. But here the main what I wanted to highlight is if you do the principal component analysis, basically we are doing the eigen decomposition of the covariance matrix, right? So here X transpose X and that size is M cross M matrix. And here eigen decomposition of covariance matrix, that is X transpose X. that is eigenvector and eigenvalue. And using these information, we will do the eigen decomposition. And then we will also derive meaningful information particular to a particular object. And we will consider all the available bands as an input. Now here, after doing this, I'll come to the table. Yeah. So once you do the eigen decomposition, what we do is we have given the input band 1, band 2, band 3, band 4, band 5, band 7. Right? This is from Landsat. Now, since we have given 7 input bands, sorry, this is 6 bands, I can have the maximum 6 principal component. So this is PC1, PC2, PC3, PC4, PC5, PC6. Now here, these are the basically loadings. So loadings of different bands. So PC1 has 22% of first band, 37% of second band, 69% of third band, 38% of fourth band, 42% of fifth band, and 12% of band 7. If you add them, it will become 100. Now, this is the principal component 1, and where we found that variance is 80.56. That means if you see, variance is very, very high in principal component 1. So that means if the variance is high, that means 81% information is available with the principal component 1. Now here, if you refer to this PC2, you'll see that negative loading. This is negative sign, means minus 6% of first band like that, and 92% of fourth band. Now suppose if you wanted to identify a particular object which has very good absorption feature in band number 4. So what I will do, I will prefer to use this particular band rather than going with the variance having 81% of PC1. This will be better for me, right? So I will be using PC2 to highlight my feature. So that is the advantage when you do the principal component analysis. So in general, this is just to understand the physical meaning. So if you see here, the first plot, it is showing the two data set, the band 1 versus band 2. Let's say consider this band 1 versus band 2. If you plot them against each other, you'll find they are having this kind of plot, right? If this is the plot, then we can easily say this is positive correlation and they are highly correlated. So what we do is we try to shift this origin here at the center of this ellipsoid. And then here, taking this as center, new center, we will rotate this one with some angle. If we rotate, this data will become uncorrelated, right? So this is what we are doing in principal component analysis. So let's say this is the band 1 of some sensor. This is band 2, band 3, band 4, band 5, band 6, and band 6. And this is the false color composite using the 3 bands. Now we have this particular table. Now based on that, this is the principal component 1. Here you can see this doesn't look like what input we have given, right? Because this is completely a new image having positive or negative loading of all the input bands, right? This is principal component 2, principal component 3, 4, right? So if you refer to object-based absorption feature and then corresponding which principal component is giving you a positive and negative loading, and if you identify a particular object using principal component, any of the principal component, This kind of analysis is known as feature-oriented principal component analysis, right? So let me see if any other question we have. Can I use the pan sharpening for image enhancement before land use land cover? See, if you are going for the qualitative analysis, you can definitely use. But if you are going for the quantitative analysis, again, when you do the any kind of digital image processing, you are playing with the digital numbers. So you have to be very, very careful. If your final results are quantitative analysis, we are not supposed to do any kind of digital image processing, right? To enhance the brightness and contrast, because that will change the actual value. But if you are going with the just object identification, and that will be like qualitative, then you can definitely do that. This is again from the what to say from the assignment, so I will not answer to it. Yeah, here we have how thermal imaging works. So how thermal imaging, I have already covered the basic this thing, uh, basic questions. Then I have joined late in this program. I have missed the assignment 1 and 3. So I think you have already asked that question and you have got the reply from NPTEL also, that we will not be able to extend the last date. So that's all from me. And let us wait for a few minutes. If you have any other question, we will answer to that. Yeah, regarding this thermal remote sensing, what happens? When we talk about the image acquisition, suppose this is your surface and this is the source of energy. So in our case, it is sun, right? Now this energy is falling on this particular surface, and here some amount of energy, as we know that interaction between the light and the object, some amount of energy will be absorbed, some will be reflected, some will be transmitted. So here the energy which is getting absorbed in any of the objects, subsequently this has to be released, right, to maintain the equilibrium with the surrounding. So if that object is releasing the energy, essentially that will be in the longer wavelength region, right? So that will be from 3 micrometer to 16 micrometer or 14 micrometer. But 3 to 5, again, we have problem with the atmosphere. So we generally have 8 to 14 micrometer images. Now here, this is the energy which is coming out from the object, right? And this energy is in the longer wavelength region. So here we can say that this is nothing, this is not a superficial property, this is a volumetric property, right? So this volumetric property will be recorded by our detector. So this here there is one major difference. Here when we talk about the reflectance, it is the superficial phenomena. But when we talk about the emittance, the emitted energy from the surface, that is basically a volumetric phenomena, right? So that is a volumetric process. So the information which this particular wavelength will carry, that will be about this whole volume. But here the information which is coming in reflected energy, that will be superficial, right? So that is the major difference between these two. So I don't think we have any other query. So maybe we can close this session. Saurabh, you can watch the landing, right? That will give you more details. That is available in DD1, as well as there are a few channels which are actually showing this Chandrayaan 3 landing. Uh, yes, during this live session, mm, which live session you are talking about? Whether it is with the TAs or whether it is the lectures. Lectures are saved. Lectures you can refer. But these live session, it happens only once or twice. So don't worry about that. We have a new question. So basically, after doing all these, what to say, analysis, you are asking about the analysis, mathematical equation. So there is last lecture, the last part of my course, there is the application part, right? So there you will be knowing like what are the areas where we can apply this remote sensing GIS, and there you will be needing all these mathematical equation and analysis techniques to get your results, right? So please be patient and finish this course. So application part is there. So there you will learn more about the application of all these equation or techniques. And yes, there are many different remote sensing GIS softwares. There, all these processes can be done by just clicking on the using that tool. You just simply click, give the input image, you'll get the output image. But in this course, basically, you will learn what exactly been done by that particular software. What approaches are out there to map flood water under vegetation using optical? See, optical will give you the superficial information, right? So your data, you cannot penetrate the vegetation. So there is no way out that you can do the flood water monitoring or anything which is actually hidden under the vegetation. So you cannot do that. That is the limitation of remote sensing. Yes, I suppose this live session is getting recorded and it will be available in the YouTube. So maybe you just have to Google it and you will find that. How to randomly separate a region into sub-regions with different areas. Your question is not clear, Saurabh. What exactly you want to do? So which data to split a watershed into sub-watershed, you need to have very good resolution data, right? What is the area or catchment size of your watershed? So based on your DM, you can split into different regions or sub-watershed. But it all depends like how, like what is the resolution of your data. So the artificial farm could be rectangular or any other shape within the watershed, you mean to say, right? So if that is so, then you can draw this in ArcGIS, there is no problem. If you don't want sub watershed, or if you just want any rectangular or any other shape, then based on your watershed, you can just draw the different polygons in your ArcGIS or QGIS or any GIS software. Related to application, I think now you have understood the remote sensing GIS, the basics part. So the application part will be covered in the in upcoming lectures. So wait till then. You will understand many areas, and even in many of the application, remote sensing can serve as very important tool to produce or provide the important information. So this remote sensing is not the complete answer, right? This is a tool to get some information which can be part of your main analysis. So that's why even in my lectures, I also told you that this is a tool, right, to acquire or to get some information which is required to get your final results, right? So this can serve as a very important source of information. Uh, for QGIS, what you can do is you can just go type or search this in Google. They have a dedicated website. From there, you can download this tool or the software and install it, and then you can use it. Some of the data sets are available, like test data set, you can download from the NASA or from the ISRO website. So some of the data set might be available as a test data that you can download. And even when you download this remote sensing GIS softwares, along with them, there are some test data sets which are available inside the software itself. So you can use them. As many of you are asking about the hands-on part, like how we will be using different softwares, or so maybe I'll see, maybe soon I'll propose a course on the hands-on remote sensing GIS, how we can do all these analysis in the software using a particular software. No, it is not required. GIS, geography, both are different, right? GIS and geography both are different things. They are not really like exactly same, right? So it doesn't matter from where you are studying, but you can learn GIS. A job is not the aim of this particular course, right? Because you need to have like when you appear for an interview, and suppose this is a remote sensing based industry or a company, they will ask the questions. There this course can help you, right? But it is not guaranteed, or there is no certification that you will get the job after this particular exam. This course is meant for the learning, right? So whenever you go and appear in the interview, questions what people will ask, so there this course can help you. Okay, thank you so much. So I don't think we have any questions. So we'll close this session now. Sure, I will try to do that as soon as possible. This hands-on course is specifically the application part, and let's see how it goes. Merging both the things like theory and practical, ideally this is good, but the course will be huge actually, because this is a complete, this is a new field. So if I merge them together, it will be very hectic. So the syllabus will be very lengthy. So that's why I'll try for the practical one. In making it 8 to 12 weeks, this will not help. I need more time for the software part or the hands-on part. Now, related to the question, which is quick explanation about the spatial and spectral resolution, how it is used with a real example. Spatial resolution is basically when you take a photograph with your camera and you just transfer that image on the system or laptop or desktop, then you can zoom it and you can see there are small square boxes, right? And you keep on zooming, they will become bigger and bigger. So those are the pixels which are forming your image. And these one pixel is basically one digital number associated with that particular pixel. This is what been captured by your sensor. So the energy which is getting reflected, that is getting absorbed by your detector, and that one pixel energy or the value has been generated. That So in other way, you can say one pixel is representing a specific area on the ground. So that's why when we say 1 meter by 1 meter, 30 by 30 meter, that means one pixel is representing 30 by 30 meter on the ground, or 1 meter by 1 meter on the ground, right? And the spectral resolution is for a given wavelength range. What is the wavelength range which we are targeting to acquire the images? So for example, 0.4 to 2.5 micrometer. This is one wavelength range. In that wavelength range, how many bands we are targeting to generate? So let's say we have targeted 5 bands. So there will be few wavelength regions which are left, because that we will not be using to generate the image. So first thing in spectral resolution is what is the overall wavelength? Let's say 0.4 to 2.5 micrometer. Then how many bands we are generating? Then third is what is the wavelength range used to generate a single band or image? So that is called the bandwidth. So you can either say bandwidth, or sometimes we also use the central band. So that will be used. So if you use all these information together, that is known as the spectral resolution, like how many bands we are acquiring in a given wavelength range with what wavelength wavelength range, right, to generate one particular image. So let's say the example part, if you want to monitor the changes in an urban area, you need high spatial resolution. If you want to identify change in the species of the forest cover, then you need high spectral resolution. If you want to monitor encroachment in the forest land, then you need high spatial resolution. If you want to identify a particular object with its chemical composition, you need high spectral resolution, right? So these are the examples. which resolution shall be used for what use case. So once you understand the resolution, we generally refer to these basic concepts so that when you have actual problem where you need information derived from the remote sensing data, you will be able to decide which resolution will be best for my application or for my information, right? So there is no handbook to this, but once you understand the resolution carefully, and whenever you need any information from the remote sensing data, then you will be able to decide which resolution is best. While your question is like you're asking few questions from uh, I think assignment or maybe from some other question paper, right? So this spectral enhancement, once you know the spectral region, right? So spectral enhancement means what exactly you have captured, how many bands you have captured using remote sensing sensors, and then how do you want to enhance that. So can you generate more number of like, so I that's why these question I will not answer because this will be like a direct answer to my questions itself. So I told in the beginning that no questions will be answered directly for the like assignment question or any other question which is coming from my question paper itself. So you need to just go through the lectures. If you just listen to my lectures carefully, I have tried my best to explain all these components with very layman language. Very simple words. I have explained all these things. I tried my best. I hope you will be able to understand all these concepts. Right? Just go through the assignment videos once again. Okay, so I'll close this session now. Thank you very much for joining this session as well as joining my course Remote Sensing and GIS, and hope you all will get the benefit and you will be able to use this in your future research, right? Thank you. All the best. Thank you.